So why midnight? Why midnight? Why are we building a new layer one as a partner chain of Cardano? What's the point? Why take all this effort and 6 years to build this thing? Well, basically, we have the thesis that privacy and ownership, you shouldn't have to give that up as basically an expense to come use a service, right? Just because a service is free and you become the product, why does that have to be the norm? Why can't we change it? Why can't we empower you to be the owner of your asset, the owner of your data, and then decide how it's used, right? If you want to distribute it to somebody and let them use it to advertise to you or pass it along as a medical record, that's up to you. Why should you give this away to some other organization and let them take control? So what we want to do is we want to enable the freedoms of ACE. So the freedoms of association, commerce, and expression. So who you associate with, that's up to you. It's not my job to get in the way or make decisions on what that should be. What you buy, what you purchase, maybe you're a big Vampire Diaries book reader. That's really none of my business. If you are into those kinds of books, feel free, but you don't want that breadcrumb left out on the internet for anybody else to see potentially, because it could be other things. And then expression, right? The art that you make, the meme coins that you make, the NFTs that you make, those are up to you. We want to empower you to be able to go do this. We want to remove censorship that could be in these types of systems. And so how do we do this? We do this with Midnight. It's a 4th generation blockchain. It's a blockchain that allows you to keep a secret. We're going to tell you a little bit about how that works as we go on today. All right, so traditional web applications. Everybody's used these. Basically, you, the user, talk to an organization or a company's application, and you transmit all of the data that application needs to service you, whatever it may be. So for example, I bet every single one of you logged in with Google or Facebook or Snapchat or something this morning, which gave a signal to those organizations about what you're doing, and now they can trace you around the internet. They can do lots of things with that information because legally it's theirs. You're giving them possession of all of that data because you're using their services. I know those services are super convenient, but you're giving it away. You're the product. So how do we change this? How do we make it so that you're not sending all of your sensitive information to somebody else and then, fingers crossed, kind of trusting them that they're not going to use it for something you don't want them to use it for? So traditional Web 2 applications are in this form, 100%. There's really no way around it. If you want to interact with these things, you're not empowered as an owner of your data. You are absolutely the product, and you are giving your data to them so that they can use it to advertise to you, to profile you, to tell other people about your activities, things like that. So somewhat of a reaction to this and somewhat of a reaction to the empowerment, Web3 showed up, right? So you got public blockchain applications, and back, oh goodness, what is this? 15, 16, 2010, we had the idea that we can change the world. We can build out a blockchain, we can enable people to interact with it, we can build dApps on top, and that'll help cure the issue that we had in Web 2. Well, it's not exactly what happened. The issue is that most blockchains are transparent, completely. Not all of them, but many of them are transparent. So you can see, at least the pseudo-anonymous, some transaction happened between A and B, and all of the information is there. And for example, if I was spending crypto on my habits, anybody in the world would be able to figure out that I got a coffee habit, right? 8 a.m. every single day, $4 comes out of the wallet to the same particular vendor. Very easy to profile a big signal. But that's not how the regular economy works. The regular economy, I wander over to the coffee shop, I use my credit card, I get my coffee, I walk away. Who knows about that transaction? I do, the barista does, knows whatever type of coffee I like, and the credit card company does. And there's other rules around keeping that information private. So that type of change is what we want to empower, is so that you can actually have economic exchange and expression and commerce in a way that you can selectively disclose what's revealed, and you can do it such that you can have point-to-point interactions that are completely legitimate, completely legal, and viable for the applications that you're building. However, in the current Web3, that's not possible. If I wanted to have a bank account that's a stable coin, held on Cardano or Ethereum or any of these things, it would give away my transaction history. And if they try to make it private, then it's often an L2, something like that, where you're trusting this other organization. So it kind of moves away from the entire ethos of what Web3 is supposed to be. So as an answer to that, we built Midnight. So what Midnight does is Midnight adds to the system the ability to have both unshielded and shielded information. So unshielded, transparent, right? The usual Web3 interactions that you see, right? The data, the metadata is all visible, right? Everybody's used to that. The shielded side, people usually think, ooh, Zcash, Monero, things like that, where there's a privacy layer, and depending on how much you read, being a privacy coin is kind of toxic. You really don't want to be one of those. However, so what do is we enable you to define the spectrum in between completely transparent and totally private that enables you to build the application that you need to build. And in addition to that, we leave the data that's used to run the smart contracts, the vast majority of it can be defined by the developer to stay with the user. So my credentials, my private keys, my books that I bought, all of that information stays with me, literally on my computer or on my phone, doesn't get transmitted over the internet to anybody, and now you can still have these interactions. And you're gonna ask, well, Ben, how in the world can we do this? And I'll tell you, just wait a minute. We're going to talk to you about what Compact is, the smart contract language that lets you do this in just a few moments. But that's part of the key, is that the information that you use to run the smart contracts, the private stuff, stays with you, never leaves. Doesn't get transmitted to somebody else, doesn't get encrypted and put on a chain. It is simply yours and in your possession. So what we can do with this system is we can protect both the data, so what's happening in the smart contract, and the metadata, the to and the from and the values that go in between. All of that can be protected, and it can be selectively disclosed depending on the application. So how does this work? Well, this is very much removes a lot of the detail, but basically you have a user, which by the graphic, the little black dot, the user's got some private data. That private data is associated with a Merkle tree that's got a bunch of zero-knowledge commitments that's held on the Midnight ledger. Ignore all of that, but basically think, I have the data. I need to be able to go interact with it. So I have to read something from the chain that's going to allow me to advance the state. That's the first step, is you go read the information you want. You use that in a smart contract to update the state. But where does the smart contract run? This is a big difference. Usually the smart contracts in most Web3 run in the chain, right? They run in the validators, everybody agrees, and the state moves forward. In Midnight, that doesn't happen in the exact same way. In Midnight, you build a proof on your side of the internet using your private data, so a zero-knowledge proof, and you submit the proof as the transaction, along with any updates to public state if there is any. So what that allows you to do is it allows you to keep your private information private. For example, if I had to go buy something, they might challenge me based off of where I live. I don't need to reveal my address, my age, my name, if I'm a blood donor, all of this other stuff to that particular application. All I need to reveal is a true or false, am I in the appropriate jurisdiction? And so I can do that with Midnight because I can build a proof based off of that challenge, and that can be submitted, and the answer is true or false. It's not Ben lives in New York. Once the proof is submitted to the chain can validate it, and can validate it very fast using the technology we have, and it creates another commitment to allow you to advance the chain. That's it. So the nice part is that the interactions start to mimic what you see in real life, right? You go and you have an interaction. I go here talking to Sam. It's between me and Sam. He might go whisper to somebody else later, but it's between me and Sam, and that's kind of the limit. It's not that somebody else that's not in this room can come and figure out what we were talking about and later use that to their benefit, or in a way that could compromise my own privacy. So I've talked a lot about Midnight. One last thing around the architecture. The architecture is flexible. The architecture allows you to build many different embodiments where you can allow the user to have a wallet and know that they're using Web3, or you can abstract it all away and it's just a website or a mobile app that they visit. You're gonna hear from Joe in a moment that we have a smart contract language that looks and feels like TypeScript. That's how you define the actions that are going to go on in Midnight. That is used to build out your dApp. As a user, you're going to pull down the circuit, you're going to run it, and you're going to submit proofs back to the chain. And you're going to notice that there is a level of trust with the computing that happens on your side that allows you to see what's going on and allows others that you want to selectively disclose this information to see what's going on. But the chain itself simply does not carry the information. So you can go interrogate the chain all you want, and you just simply can't figure out the activity that's going on. So how does this relate to Cardano? So Midnight is a partner chain, and specifically Midnight buys 3 things from Cardano. So first off, any SPOs in the room? Oh, we got a couple. All right. So all of the work that you've done to get delegation assigned to your SPO, right, and go out and market and get everybody encouraged and keep the system up, you get to continue to leverage that because that distribution will be used to figure out if you want to operate a validator on Midnight when you get to produce blocks. So if you got a fully saturated SPO already, you get to reuse that in Midnight, and all of that effort you get to keep pushing forward, and you'll have a higher level of kind of getting chosen to produce blocks as if you had a lower. In addition to that, you may have heard, and you're going to continue to hear, that we launched the Glacier Drop this week. So feel free to come and claim your night. If it's on any of the 8 ecosystems, it's there, it's ready and waiting. You got 2 months to come and get it, so you don't got to go out and rush and get it right now. But that token and all of the utility that it's going to leverage is on Cardano. So all of the DEXs and lending applications and everything that's on Cardano can manipulate the Night token because that's where the vast majority of it is going to be dropped. So there's going to be transaction fees that show up just simply from Night moving around. And then the last element is when you have Night, you're able to generate dust, which is the fuel for the system. That generation is a transaction. You have to state, I want my dust to go over in this wallet, wherever that may be. So there's more fees that show up. So simply by having Midnight as a partner chain of Cardano, there's these 3 different types of revenue that are going to show up for the SPOs to enhance the operation. And so we hope, as we roll this out, come and join us and become part of the validators. With that, I'm going to turn it over to Joe Denman, who's going to talk to us today about Compact. So please welcome Joe.
Thanks, Ben. My name is Joseph Denman. I work on the compiler team at Shielded Technologies on Compact. Compact is Midnight's default language for creating privacy-preserving contracts. By show of hands, who here is a developer? Mostly developers. Excellent. Who here has familiarity with ZK technology at all? Cryptography at all? Awesome. OK, so I think this is the right audience. So we're going to talk about Compact today, but I'm going to spend very little time on the surface aspects of the language. I'm going to show very little of the source language. Towards the end, we'll do that. I'm not going to run the compiler, and I'm not going to go through any significant example. And the reason I'm not doing that is because instead I'd like for you all to walk away with an understanding of what the fundamental insight behind Compact's programming model is that allows it to actually innovate. So to do that, we're going to essentially do ZK-SNARK 101. For anyone who's familiar, hopefully it'll still be fun. After that, I'm going to tell you what we tried to accomplish with the language. We're going to go through the public-private dichotomy that we sort of see in Midnight. We're going to look at Kachina. I don't know if you guys have read the paper, but it's the formal model on which Compact is based. Then we're going to talk about transcripts, impact VM. We're going to run through the language itself, and I'm going to end with some cool tools that we've made to make Compact developers' lives easier. OK, so this is going to be textbook, but you kind of have to go through it when you talk about ZK stuff. So ZK-SNARK is a protocol by which a prover can convince a verifier that they know the solution to a problem. And there's lots of ways to dress up this definition technically. Obviously, I'm lighting a bunch of technical details here. But we call the solution the witness, and then the problem, referred to as X, the statement. And then sort of the most striking property of ZK-SNARKs, one of the reasons why they're famous, is the zero knowledge condition. So something is a ZK-SNARK if it satisfies these conditions. Zero knowledge being 1, which is that the proof doesn't leak what the witness is. So you can prove something, you're not leaking what the actual solution to the problem that you're proving is. Succinctness, also one of the more useful properties that we find leveraged mostly in L2s, which is that you can verify a proof really, really quickly, polynomially, actually. Completeness, if you create a valid proof, then it should always convince the verifier. And then soundness, to create a valid proof, you actually need to have known the solution to the problem that you're proving. And one of the seminal results in the space by Goldreich and others in 1991, which is that you can create a ZK-SNARK for any problem in the NP complexity class. And this is a pretty striking result, right? It takes a little while for it to sink in. There are so many problems, so many of the problems that we talk about regularly are in NP. And so I think it'll be fun to go through actually how they prove this briefly. So it starts with this problem called graph 3 colorability. And the problem is this. Given a graph like the kind on the left, assign a color to each node such that every node has one color and no two neighboring nodes have the same color. And so a proper 3 coloring is the graph on the right. And so what you can do, and what they did in this paper is they said, for this particular problem, we can construct a ZK-SNARK protocol, which is, given a graph like the kind on the left, if I know a coloring, I can prove to you that I know the coloring without telling you what that coloring is. And so they proved in the original paper that there is a protocol for this. So it turns out graphs like the kind on the left actually correspond to expressions from Boolean logic, which is logic with negation, conjunction, disjunction, et cetera. And so I wrote a script, and the graph on the left actually corresponds to the expression on the right. And there's another problem called 3-SAT. And the problem is this. Given a Boolean expression like the kind on the right, find a truth assignment. Oh, by the way, these are variables. X, yeah. So find a truth assignment to every variable such that the entire expression becomes true. And this is what's called NP hard. So any other problem NP can be stated in terms of this, right? And that's from Cook-Levin, 1971. And so if you have a ZK-SNARK for 3 colorability, and 3 colorability is isomorphic with satisfiability, and immediately you get a ZK-SNARK for everything in NP. And just for fun, there's also a conversion from these expressions on the right to what we call arithmetic circuits. Arithmetic circuits are where essentially you have a bunch of gates. Gates represent arithmetic operations. And I wrote a script to do that too. And that's what it looks like. So everything, each of those yellow nodes is actually an arithmetic operation. And so for any of you who are familiar with ZK, this is how you start to get arithmetic circuits to appear in the ZK literature. So that is a whirlwind tour of ZK-SNARKs. Let's talk a little bit about Compact. Design goals. The large majority of this talk is actually going to focus on the first. And the primary goal, the primary innovation of Compact is public-private data interoperability. We want to have first-class support for accessing external public and private systems from within Compact. Second, safety. Privacy is notoriously nuanced. Reasoning about privacy is. And so if you're going to allow public-private data interoperability, they need to provide tools to help the developer along the way. And then third is familiarity. A lot of circuit languages, especially in the blockchain space, resemble Rust. And that's because most ZK-SNARK libraries are written in Rust, and it's sort of a truism that languages tend to resemble the languages that they're implemented in. And so we didn't want a Rust-like language. We wanted a TypeScript-like language because most D app developers are fluent in TypeScript. And so we wanted to have a TypeScript feel. But as I say, most of what we're going to talk about today is public-private data interoperability. OK, so the main problem. In these sort of ZK smart contract systems, you always, in my experience, I think by definition, but especially every time that I've seen, you have some sort of on-chain state, and then you have some sort of off-chain state. And then you have some sort of circuit language that's going to prove the correctness of interactions between the two domains. And these have two major problems that I've seen. The second is inherent, and the first is not. OK, so how to state this? OK, so arithmetic circuits are an inherently limited computational model, limited expressivity. When you're in a circuit, you normally only have access to bounded length data structures, bounded iteration, bounded recursion. And so what we've seen is in circuit languages most of the time, if you want to do a joint update of some on-chain and off-chain state, and you're in a circuit language, you have to do all of the computation in circuit, which means that the sort of private state transformations that you can do are limited and potentially blows up your circuit size depending on what the shape of your private state actually is. So that's problem number one, the inability to escape the circuit context. Problem number two is going to be one that's more familiar to Cardano developers. And the problem is this. You have a piece of on-chain data. It's chattering with concurrent updates from other users, submitting their transactions. You want to build a transaction. You take a snapshot of the data. You build your transaction off-chain. And by the time you've submitted your transaction, the data has changed, so your transaction is rejected. In the ZK languages, ZK blockchain space, the problem is actually a lot more onerous, because sometimes proving takes literal seconds. And you can't afford to reprove your transaction every time your state snapshot becomes outdated. So yeah, these are the main issues: inability to escape the circuit and race conditions. And so I'm going to tell you how we address these two. But first, I'm going to introduce Kachina. Kachina is a mathematical framework introduced by Thomas Kerber in 2020, one of the technical architects on our team, for defining privacy-preserving smart contracts. And the innovation in Kachina is that it allows you to precisely, mathematically, define which aspects of your contract are private and which are not. And once you have that definition, then you can prove formal security properties. And so Compact is a realization of Kachina. In Kachina, a contract consists of a set of transition functions. It has some sort of public subsystem. A contract has some sort of private subsystem. Transition functions communicate with both of those subsystems and record those interactions. And so Compact is a realization of that. In the public, for the public subsystem, that's essentially instantiated by what we call Impact VM. And this is the on-chain portion. Impact VM code is public code stored on-chain with a public state. The private subsystem is instantiated as TypeScript, TypeScript code that lives on the user device that maintains its own device local state. And then finally, the transition function becomes the circuit language, a ZK circuit language to prove the correctness of interactions between those two. Something which may not be obvious to anyone who isn't familiar with the Midnight architecture is that on Midnight, the public ledger is an account model, at least with respect to contracts. So every contract has an address which stores on-chain code and has some on-chain storage. And the key innovation introduced in Kachina is this notion of a transcript. A transcript is going to allow us to escape the circuit context and re-enter it. And it's going to allow us to mitigate public state race conditions. A transcript is simple, just a record of interactions between the circuit and some sort of external system. You have two of them, a public transcript for public interactions and one for private interactions. And in our case, The public transcript contains a series of impact VM calls. We'll talk about impact VM later. Louder. OK. The private transcript is a series of TypeScript calls. So the key insight here is don't prove against a public and private state input. If you try to prove against public and private states, then you suffer from this inherent public state race condition sort of thing. Instead, what you want to do is you want to prove against operations on the public and private state. And so remembering that ZK-SNARKs give us a way to prove that we, yeah?
Could you give an example? What would be the proofs against state and operations? Like, just a brief example to get it.
Sure. OK. So is some of, let's say, OK, so let's say in StarkNet. Are you familiar with StarkNet? No? OK. So StarkNet is StarkNet's a scaling network for Ethereum. And they also have a snazzy circuit language. On-chain state, they keep, and which is actually pretty common in scaling solutions, like in LT. You will compress chain state into a Merkle root, right, and store that on-chain. When you want to update the state on-chain, you'll take a snapshot, typically, of the state, which may include an input as the Merkle root. You'll compute Merkle root after your updates have completed, and then you'll publish the new Merkle root. And so if the Merkle root changes in between the time that you've created your transaction and the time where it's actually applied, then your transaction is invalid. And so in this case, what we're talking about state, yeah, becomes sort of a Merkle root. If that, was that?
Yeah, but what's the operations then?
Oh, you want to know this? Yeah, we're going to talk, I'll go through the specific operations. Yeah, I have code back, yeah. Yeah. So yeah, I don't want to dive too quickly into concrete stuff because without a circumspect view, it actually doesn't make much sense. But yes. OK, so let's move on. I'm going to show you two diagrams. There isn't really a single succinct diagram that's going to really impress upon you the full thing, but we can try here. Let's start in the top left. In the top left, we have our compact source program. And what we're going to do, sort of first, is we're going to compile that program into two artifacts. We're going to compile it into a JavaScript executable. This is contract.js. That goes straight down. And we're going to convert it, secondly, into another artifact called ZK-IR. ZK-IR is what we're actually going to feed to the proving system to create our circuits. So let's look at the bottom part first. In Compact, building a transaction is a two-part process. You first execute some JavaScript, and after that, you pass some of the artifacts produced off to the proving system to create a proof. And so the contract.js, for example, is going to interface both with Impact VM and also with a box down here on the left called witnesses. Witnesses are user-defined code. That's the private part of your application. And when you execute your contract, which contains your circuit, it's going to produce two things, as I mentioned, public transcript, private transcript. Remember, these are just records of operations. All right, let's look at the top side. The ZK-IR, and this all happens compile time, is converted into a QAP. For anyone familiar with ZK, that's quadratic arithmetic program. It's what we use for proving. A circuit representation we can use for proving, which is going to produce a prover key and also a verifier key. The private transcript and the public transcript serve as the statement and the witness, which we're proving, right? So the private transcript, the list of operations, the list of private operations I performed, this is going to be the public transcript is going to be what's public and submitted on chain. So given a private transcript and a public transcript, I can produce a proof. I can batch the proof and the public transcript into a transaction and send it on chain. What the node's going to do when they get that, they're going to verify the proof, and then they're going to attempt to reapply the same operations that were performed on the user device. And so we have this two-part structure in Compact. We have collecting transcripts, creating proof, and then attempting to reapply the transcript. And I'll show you a little bit more about this sort of going forward. I was going to show this slide. Now that I'm thinking about it, it actually is the most technically accurate way to sort of describe this whole protocol. But maybe we'll skip this one. The important point that I want to impress here, and this is all sort of going back to how transcripts allow us to address public state contention. You have two important aspects here. This is a user device on the left, node device on the right. The important bit is you fetch a snapshot of the public and private state. These are the first two lines. You execute your circuit in the form of JavaScript. You get your record of operations. You create your proof, and then you submit your transaction. And on the node side, the first thing that you do once you get the transaction, attempt to verify the proof, and then attempt to apply the transcript. So collect transcript, reapply it. This has some implications for the sort of operations that you can have in your transcript. All right, and I promise after this we'll look at it in an example. So Impact VM. The operations in the public transcript are instructions in Impact VM. Impact VM, which you might find surprising, operates on rich ADT sets like sets, maps, lists, high-level data structures. And it includes high-level operations like map lookups, set insertion, counter increment, et cetera. We need to, if we're going to have a transcript that is actually replayable, prioritize operations that are coarse-grained, and we prefer those that are commutative. Commutativity because applying something or applying an operation locally, there's a good chance that it can be applied remotely as well. OK, so here's some code. And this is jumping forward a little bit. But this is an actual Impact or an actual Compact program that you could deploy. It doesn't do anything interesting, but you could actually deploy this. The on-chain part of the contract, the on-chain storage, is actually just a single field here. It's indicated by ledger. A single field M. This indicates that we have M in the public state. And that particular entry is a map. It maps field elements to field elements. Field is a primitive in Compact, which is just an element of the underlying scalar prime field of the proving system, but it's essentially a number. So this is a simple entry that maps fields to fields. And this contract has one circuit defined, which is foo. Foo is publicly callable, and it only does one thing, which is insert a mapping from 1 to 2 in M. And so what you would do if you invoked this function is to just see that effect. And so when you do the off-chain portion of execution, the public transcript that's produced will just have one entry. And that entry will be a single pair, which is the instruction that was performed, in this case, an insertion, at ledger declaration 0, that's M, of 1 to 2, right? And then the second part, which is the square braces, that indicates the result. But this is just an insertion, so it doesn't have a result. Imagine what a public transcript would have looked like if we chose Impact VM to be a register-style machine, where every time that you want to modify some part of the public state, you have to do a load or store operation, right? Imagine trying to accomplish something like a set insertion in register instructions. There is no way that by the time you create your proof, submit your transaction, if that state is public at all, that none of the addresses that are involved in those instructions would have values changed, right? And this is what I'm trying to get to about replayability, public state contention. By using high-level operations with lots and lots of semantic information included in them, we can strike a balance between usefulness and replayability. OK, so this is one example. That's just a map. Here's another example. Let's look at the top circuit first. Same deal. Circuit definitions. These are public. Here what we have, ledger X, this is actually just essentially a mutable variable. So it behaves a lot like a class variable from object-oriented programming. And you can assign, you can read from it, et cetera. And foo is even less interesting this time. All it does is assign the value 1 to X. And so the transcript here would just contain a single instruction, which is write at the first ledger declaration, 0 indexed, so 0, the value 1. And this will always succeed when you attempt to replay this, right? This transcript will always succeed. The second one is an example of a transcript that might actually not be able to be replayed. So the function bar, this is going to have 2 instructions in it. On the right-hand side of the assignment, you'll see the X occurrence. This is evaluated like an expression, so just a reference. This says read ledger declaration at position 0, so read X. And the second part of the pair is the result that you get back from it. So say X actually maps to the value 10 right now. Reading X, getting the result back, which is 10. That's the first operation. The second operation is write at ledger declaration 0 the value, which is 1 plus 10, so 11. And this is a transcript that likely could fail, because the first time that you do the read locally, you might get 1 result. If anybody modifies it concurrently to a different value that is not 10, then the transcript application will fail. And so the entire transaction is rejected. OK, so if such a simple update could fail replayability, how do you actually achieve this in a compact program? This is a very simple kind of operation that you would like to be able to perform. And for that, we have a counter ADT. A counter ADT supports increment operations, but does not require 2 instructions to actually execute. So here we just have a single increment instruction that accomplishes the same kind of thing. And so we have this custom suite of ADTs that we use Impact VM to implement. And this is sort of how we get to mitigate the issues of public state contention. All right. So now I'm going to blow through some of the syntax of the surface language. Most of this information is on our website, and so anyone who's interested can go through the developer docs. Some facts about Compact. Compact is strongly statically typed, bounded, meaning typically it operates over bounded data structures and has bounded recursion, bounded loops, similar to most other ZK circuit languages in the space. And there are 3 sorts of declarations, high level, that correspond to the public-private aspects of the contract. Ledger declarations, which we've already seen, correspond to declarations of public programs. These are the ADTs that we've seen. Witness declarations, these are essentially just stubs. And this is how your circuit can, or how you can escape your circuit into TypeScript. Yeah, witnesses are essentially an FFI into TypeScript from the circuits. And then circuit definitions, which we've also seen, essentially just do calls to either of these 2 other declarations. Primitive types, if you've looked at any ZK languages before, these will be very familiar to you. We have Boolean values, in-bit unsigned natural integers, field elements, giving you clock arithmetic. This is the scalar prime field of BLS 12381 from the underlying proving system. We have tuples. They're tuples. Vectors of fixed length. So the first parameter being the static bound on the vector length. So n would be 32. T could be any other variable or type from the language. Bytes, n-length byte vectors. Bytes have a different representation. They're compacted by the proving system, which is an optimized form. And then we can represent string values, but you can't do much aside from publish them, at least for now. You can do user-defined structs. The only restriction is they can't be cyclic. We have modules for structuring code, definitions, sort of facilitating for packaging, library authoring. And then what every popular ZK language needs to have, const assignments and assertion expressions. And so we didn't get to spend much time on the arithmetization process, but we use Halo 2 in the back end, which means that we use Planckish arithmetization for these sorts of circuits. Fun fact. Conditionals, if conditionals, ternary conditional operators. So if conditionals, if else's, fairly straightforward. We can do maps and folds and iteration, again, over bounded length data structures. And these are all, so the way that you accomplish these in these languages is essentially by loop unrolling. So because we have static bounds, we can expand all of these by inlining the various stages of the computations. Finally, the witness language. Witnesses are defined much like circuits in the original, much like circuits from the circuit language. The only difference is they don't have any implementations. These are just stubs. So any argument that you can pass to a circuit, you can pass to a witness. Same thing for the return value. Any value you can return from a circuit, you can return from a witness. And what's interesting to see here, which you would see if you looked at our developer documentation on writing useful dApps, which we have, is that each witness declaration in the source program corresponds to an implementation that the dApp provides. And the way that we provide this implementation is through TypeScript. So from the contract on the left, we would have generated some sort of JavaScript class called contract, in this case, that actually implements the circuit logic, right? Implements all the code, does all of the transcript gathering, executes the circuit logic so that you can build your transaction. And so you need to provide implementations for these witnesses. And this is where all of the customizability in Compact comes from. You can provide your own witnesses, and those witnesses operate over a state that the user provides. The user is free to do with their private state whatever they want. But in this case, foo and bar are essentially like finite state transducers. They take a private state as an argument. They take the argument indicated in the source program. So here, the argument, for example, to foo is x, which is a UN16, which is why on the right, you have to provide an implementation for foo that takes a private state and x, which means the representation of UN16 is actually big int in TypeScript. And then what it does is it returns an updated private state and whatever the witness is expected to return. This one is pretty stupid. It doesn't do any private state update. But in these witness definitions, you're free to do and modify private state however you choose. It doesn't need to be Merkleized. It doesn't need to have any particular form, except that it needs to be representable in TypeScript. And this is where the sort of generality of Compact's approach to witnesses sort of comes from. Same for bar. And then you just call them. You can call witnesses anywhere that you can call another circuit in Compact. We already looked at some of the ledger ADTs that we provide out of the box, but this is what we have right now. Cells, those are mutable fields. Counters, sets, maps, lists, Merkle trees, and then historic Merkle tree, which allows tracking the root history for a Merkle tree. And each of these have a set of operations that are sort of optimized for replayability. Tooling and libraries. So the Compact standard library, and you can find this documentation online, includes typical utilities that you'd expect for ZK language, utilities for hashing, performing commitments, shielded and unshielded token management. So Midnight supports both shielded and unshielded tokens. And we provide utilities for receiving, transferring them from the standard library. Stuff like block time. But anyway, there's a lot of the main utilities that you'll need to write an application already exist in the standard library. What I'd like to end on is one of the tools that we created for Compact. If you make it easy to modify public and private state from within a circuit, you also make it easy to intentionally make private data public. And so we saw you can essentially update a contract's on-chain public state by just writing a value from within the circuit. And you can also access private data just by calling a witness. And so to help developers along, we created a static analysis pass of the Compact compiler, which we refer to as the Witness Protection Program. And so the example that I showed you on the left is actually, oh, I forgot I didn't show you. Yeah, I didn't include in this example the actual syntax. But the examples that I've shown you so far are actually programs that wouldn't compile. This program wouldn't compile because when you run the compiler, it will tell you that you are taking a value which is currently hidden, which is the input to the circuit. Proving hides circuit input values. And it's just assigning it to a piece of, or the contract's public state, which means now the entire world can view this. And so if you tried to write this program, what Compact would tell you is that you have a witness value, potentially disclosed. It'll tell you which line it occurs on, line 4, chart 20, and that the ledger operation that you're performing with it will potentially disclose the witness due to the right-hand side operation, the assignment operation being performed. And so there's an actual syntax that you use to indicate when you're intentionally disclosing what is currently a private value. I didn't include that in the syntax, but I'll make that correction later. So yeah, and so it'll yell at you when you disclose a circuit parameter. It'll also yell at you when you disclose the result of a witness, bar here. Same pattern here, you're just assigning the value of a witness directly to some portion of the public state. And the compiler will tell you, and it'll sort of guide you into the syntax changes that you need to make in order to indicate to the compiler that, yes, I definitely want to sort of do this. OK. We have a call to action, how to get started, a bunch of links. Ben, you want to jump back in? Thanks.
So we're letting Joe off the hook at the moment, but he'll be here all day, so feel free to come and grab him with any questions that you have. I'm sure you'd enjoy it. So how do you get started? First off, you can come to the docs. Obviously, those are out there for you to come and learn. Midnight.network, docs.midnight.network. That's where you're going to find everything you need. We also, as other ways of training, kind of your first interaction with Midnight up to your first app, we have the Developer Academy, and we have representatives here from our DevRel team that could absolutely get you introduced. Stev, Lauren, Samantha, who's here somewhere. We have hackathons, ongoing hackathons that are virtual kind of all the time. However, we also have in-person ones, one later this month down in Buenos Aires. So if you happen to be in the region, feel free to come show us the creativity that you have. And last but not least, earlier this week, we launched the Glacier Drop claim portal. So come and claim with your Cardano, Bitcoin, Ethereum, BAT, XRP, Avalanche, gosh, and two others that I can't remember at the moment. So thank you all for your time today. There are many of us here all day. Just come find us, and we'll be at Rare Evo for the rest of the week. Thank you all.